So if people will line up at the mics, I have questions as always, but I imagine you do too. Hold up your hand, and someone will come and grab a mic and give it to you.
Yeah, hi. A question for Daniela. I might be stepping on a minefield now, but I just want to simplify it. I have memory, I have an emotion attached to the memory. And I feel like, at least personally, that emotion with time kind of fades, but the memory stays. And let's say, particularly, let's say good or very bad memory, like I fell in love first time, I get back to that beach where that happened, maybe 6 months later, I still feel the emotion. After 10 years, it's just a place where I fell in love, so the emotion kind of goes away. Is that, why does that happen? Or I don't know, what are your thoughts on is because we rewrite that memory constantly and kind of change the emotion towards it, or
yeah,
how do you
That's exactly how healthy memory works. And this is through the process of reconsolidation. This is why we're actually doing that every day. And people with traumatic memories, that's exactly what is not happening for them. When they retrieve the memory, they feel as if it's the initial memory, as if they're back in the original event, because the reconsolidation process is dysfunctional. It's important to separate between the content of the memory and the emotional memory. We have different memory systems. We can change memories at the emotional aspect of them, the emotional memory. Content is a little bit more tricky to change. What usually happens is that we just confuse the content. We insert information or supplement information. And we can also do it in other types of memories.
Question from this side, perhaps? Thank you.
Jamie Truman, I'm with the Technology Exchange Lab, and I have a question for Ed. So how do you see some of your work being integrated into early abnormal brain development and perhaps catching some of these brain disorders early on in life, perhaps in children?
I guess there's a couple of short answers to that, and many long ones. Already the technologies are being used to study in animal models of brain disorders, and there's been a long history where people have questioned the utility of many of them, but with all the sequencing of genomes that's happening now, and also advances in genome engineering, one of the TR35 winners this year was Fang Zhang has been pioneering ways to edit genomes so that you can mimic human mutations from patients. There's a lot of excitement that these sort of second generation, more realistic models will allow things like understanding how circuits change and how molecules change. It's still not the human brain, but you can sometimes learn principles, and for things like development that take long times to study, you can learn some very foundational principles from models that are hard to if not impossible sometimes, to acquire in humans with longitudinal studies. From a direct interventional standpoint, neurorecording technologies, like the kind that we've developed with the electrode arrays, those are already starting to be explored for human translational use. We've started the IRB process, for example, at a couple hospitals. And in neurosurgical settings, one can imagine recording activity in the brains of patients who are having, say, epileptic resection of various regions of the brain. And during such studies, one can also conduct other studies of cognition or emotion or other kinds of things. And so we're starting to reach out to the community to try to learn about what kinds of experiments people would want to study in these rare but controlled environments of neurosurgical settings. So in the short term, those are some of the key areas.
At Research Pays asks over the internet whether there is a limit to our ability to store long-term human memories. If we're like a computer with a gigabyte limit, would someone like to take a shot at that? Steve?
Sure. The answer right now is no one knows.
Yeah.
I mean, when you think about how many gigabytes or terabytes of information go into your brain when you're just walking from here throughout MIT's campus, it's unbelievable how large that amount of data actually is. So right now, I think with the current state of neuroscience, nobody actually knows what the storage capacity actually is of the brain. But when you think about 80 to 100 billion brain cells multiplied by like 100 trillion synapses, of course, you're going to have large storage capacity.
Please. Here we go. Thank you.
Chris Meyer from NERV. And for Ted Berg, you observed and replicated a transform from these two adjacent areas. How generally can that process be applied to other parts of the brain? And if the answer is relatively generally, how many of those transforms would you have to have modeled to model a brain?
Yeah, very good question. I think that, well, first of all, the approach can be applied to other parts of the brain very readily, and we've actually kept an eye on generality of the approach with that in mind. That if we can look at transformations at particular, these are high order nonlinear transformations. If we can think of those as being the basis for, well, we've proven that they're the basis for long-term memory, then you could also think that the same types of transformations are the basis for any other kind of cognitive state. It's really what I would guess would characterize the difference between two cognitive help me two cognitive states, I guess, or episodes, is the nature of the transformation and, of course, the nature of the inputs. Right. So if we're looking at nonlinear transformations in the visual cortex, of course the inputs are different because they're what's been extracted from the visual field after several different layers of the visual system have processed that information. But it's what the result is perception. If we look at the same thing in the hippocampus, well, the data coming through are the data that's been extracted from all other parts of the brain, and the result of the transformation is long-term memory. So there's no reason to think that that basic approach couldn't be applied to almost every other part of the brain, and with a fundamental understanding of what cognitions are all about.
Let's try and take two more questions if we could before we go to lunch. This lady here in the front, please.
You'd be able to hear me, but no one else would. Hi, I'm Betsy Devine. I'm a blogger. I wanted to ask Daniela in particular about the use of scaffolding for memories for older people that start to lose some of the memories that they've had, and they can become very confused, disoriented. And have you got any suggestions, or does your research, or anybody else, give any good ideas about how to repair or bring back some of the memories, perhaps with showing them photographs, things like that? Thank you.
What's interesting about the way memory deteriorates over time is that actually the older memories, the most ancient memories, these are the memories that survive, and especially memories that are triggered by sensation and smells. This is because these are the memories that are most widely and represented in the brain. And new memories are more fragile. So basically, the way we retrieve memory, we talk a lot about storage problem. It's not that we store whole events. We actually store components of the memory, and each time we retrieve it, we reconstruct. This is why it's inaccurate and prone to interference. And the more we reconstruct the memory, the stronger it is. There could be some cognitive training. But in Alzheimer's, it's also about a biological problem, so it's more complex than that. But in principle, to enhance memories, the more we retrieve them and work on them, the stronger they get.
We have time for one more question, so it needs to be the smartest question of the morning.
That'll inhibit everybody.
No pressure, however.
All right. Luis Rogasoy, biotechnology and biopharmaceutical consultant. Although not quite the same, there is an analogy between memory and other cognitive skills and cognitive processes. Have any of you started looking as to whether those quote-unquote aptitudes or cognitive processes can be engineered?
Ed?
So there are a lot of people interested in, for example, cognitive enhancement for a wide variety of things. In fact, there's companies that have been developing software packages and trying to explore whether these things are possible. Although the field as a whole is still very controversial, and you see people back and forth publishing papers on this strategy works, this one doesn't, and I think part of the issue is that when we start talking about human intelligence in the generality of it, it becomes an incredibly complex thicket of functions. And so in some ways, if we think about the kinds of phenomena that we can study in the laboratory and the kinds of things that can be engineered now, there are specific subcomponents of this overall cognitive framework that we kind of have that operates our daily experiences, I guess. And so whether you can sort of augment general intelligence and creativity or that kind of thing is still up in the air. There are some pockets of endeavors where people have claimed to have enhanced things. For example, there was a study that came out a couple of years ago, which was very tantalizing, where they passed currents non-invasively through the heads of human volunteers and were able to, in that one study, to try to boost the probability that people would have flashes of insight, for example. But one could argue it's still very early days, and even how to define insight and what kinds of things comprise insights, and is it binary, all on or off, or is it gradual? There's just a lot of stuff that needs to be well defined.
Ladies and gentlemen, a warm hand for my panel, please. Thanks a lot. Thank you. Thanks.